Hello friends and welcome back to Techmine Guru. I am Supratim, your coach from Techmine Guru. Today we are diving into lecture 9 of our DSA series. And trust me, today's topic is the backbone of computer science. We are talking about sorting basics, which is the art of order and optimization. Often we think sorting is just about arranging numbers 1, 2, 3, 4 like this. But in the world of data structure, sorting is not just about arrangement. It is the key to optimization. It makes complex problems simple. So without wasting any time, let's get started. So what is the agenda for today? So the agenda for today will be understanding what is sorting, some DSA problems on sorting, and some basic sorting techniques like selection sort and insertion sort. So let's start with the first thing first. So what is sorting? Arranging data in increasing or decreasing order based on specific parameter. So here in this array, if you see, the array elements are from smaller to bigger. So this is ascending order sorted. In the similar fashion, this is descending order sorted because the array elements start from the bigger element and continuing to the smaller one. And similarly, this one is also sorted on the basis of number of factors. So if you see, 1 will have 1 factor, 13 is a prime number, so it will have 2 factors. Similarly, 9 will have 1, 3, and 9 has 3 factors. Similarly, 6 will have 1, 2, 3, and 6, 4 factors, and 12 will have 6 factors. So we have sorted the original array on the basis of number of factors individual element has. So now, before we write long algorithms, let's look at the toolkit. As a developer, working smart is essential, right? So every time we will not reinvent the wheel, and we will start using the inbuilt sorting techniques of different languages. Like arrays.sort is used in Java. ARR is a static array. Similarly, for dynamic array, we are using ArrayList, and for that we use collection.sort. Similarly, if you choose C++ as your programming language, you will have sort function, which will take 2 parameters ARR and ARR plus n, where n will be the length of the static array. And if you have a dynamic array, which is called vector in C++, you will have 2 parameters inside the sort function as array.begin and array.end for sorting. And in the similar fashion, for Python, we have array.sort function. And all this inbuilt sorting techniques has time complexity of O of n log n, because internally they use the most optimized sorting technique, which we will cover in the next classes. They can be using internally some merge sort or quick sort, or maybe the best of the both worlds. So now let's start with a problem where we can apply the sorting, right? So the problem says we have been given n elements and we have to remove one at a time, and the cost of removing will be sum of current elements present in the array, and we have to overall minimize the total cost, right? So if you start with a brute force and you start randomly removing, so let's take an example for that. So if you have given an array 2, 1, 4, and if you remove 2, so when you remove 2, what will be the cost? 2 plus 1 plus 4, which is equal to 7. And when 2 is removed, you have 1 and 4 left in the array. Now you randomly remove 1. So the cost will be 1 plus 4, which is 5. And now you have only element left, will be 4. So the cost of removing will be 4 only. And what will be the total cost? 7 plus 5 plus 4, which will come around 16, right? So can we remove strategically? So for that, we have to do one observation. So in this, to minimize cost, we have to delete elements in decreasing order, right? So suppose if we have taken an array A of A, B, C, T, and where we say that A is greater than B, B is greater than C, and C is greater than D. That means the array is in descending sorted manner. So what will be the cost when you want to remove it in D, C, B, A? So if you want to remove A, it will be A plus B plus C plus D. That means A is gone now. Now when you will remove B, it will be B plus C plus D. Now B is also gone from the array. Now while removing C, the cost will be C plus D. And similarly, after removing C, the only element left will be D. So cost of removing D will be D. So what will be the total cost? 1 A, 2 B's, 3 C's, and 4 D's, right? So did you find any pattern in this? So to minimize the total cost, we have got something as generalized formula. So for removing a of 0, considering the fact that we have already sorted the array in descending order, so cost of removal will be 1 into a of 0 plus 2 into a of 1 plus 3 into a of 2 and similarly n into a of n minus 1, right? So what is the general formula which is coming? I plus 1 into a of I, and summation of this will give you the minimum cost. So let's understand the code for this. So we have sort descending function which you will implement in your own language. As I told, that inbuilt sorting algorithm will give n log n. Now we will take a answer variable for the cumulative addition of all the elements for the array, right? Now just we will apply the above formula as it is. So answer plus equal to I plus 1 into a of I, and the cumulative sum of this will give you the minimum cost to remove all the elements from an array in decreasing order. So since I have already told that sort descending function, if you use the inbuilt method, the time complexity will be n log n, and this is one for loop running from I is equal to 0 to n minus 1. So the time complexity is O of n. So the total time complexity will be O of n log n plus n. And here we will consider only the dominant term, which is n log n. So the total time complexity will be O of n log n. And since we are not taking any extra space, space complexity is O of 1, right? So this is a lead code problem of finding minimum cost to remove array elements. I have mentioned the same in the description as well, so that you can also practice it. Now let's start with an interesting problem, count of noble integers. So let's first understand what are noble integers. An element in array is called noble if number of elements lesser than the element is equal to the element itself. And we have to find the count of such noble integers in the array. So let's understand that with an example. Suppose we have an array of -1, -5, 3, 4, and -10. So how many elements are lesser than -1? -5 and -10. So this will be 2, right? How many elements will be lesser than -5? Only -10. So this will be 1. How many elements are lesser than 3? -1, -5, and -10. So the count will be 3. Similarly, for 4, how many elements are lesser than 4? -1, -5, 3, and -10. 4 elements. And how many elements are lesser than -10? 0. So if we go through the definition again, which tells us an element in array is called noble if number of elements lesser than the element is equal to the element itself. So if you see, this is satisfying the criteria and this is also satisfying the criteria. So we have result as 2 noble integers present in our array. So let's start with the brute force approach to solve this. So we take an answer variable to count the number of noble integers, and we start a loop for I is equal to 0 to n minus 1. We are taking c is equal to 0 so that we can check how many elements are lesser than that element. So for this, we will start checking that how many elements are lesser than that, right? So we will run a loop from for j is equal to 0 to n minus 1, and we will check if a of j is greater than a of I. Then we will keep increasing the count for getting the count, which will tell that how many elements are lesser than that element. And once we iterate the loop, we will get that this particular element will be greater than how many elements, and just we will check that if the count is equal to a of I, we will mark it as a noble integer. So we will keep increasing the noble integer count. So what is the time complexity of this? Since we are running 2 loops, one from I is equal to 0 to n minus 1, and second from j is equal to 0 to n minus 1, for checking how many elements in that array is lesser than the particular element. So the total time complexity will be O of n square. And since we are not taking any extra space, the space complexity will be O of 1. But we are not satisfied with this. We can do something better than this. So let's see the optimized approach. So before seeing the optimized approach, let's understand. So if we have sorted the array in ascending order, a of 0, a of 1 up to a of I. So if you see, all elements from a of 0 to I minus 1 are lesser than a of I, since we have already sorted in ascending order. And similarly, we will see all elements from a of I plus 1 to n minus 1 are greater than a of I. So if we understand this, which means how many elements will be greater than a of I? Since our range is from I plus 1 to n minus 1, if we apply the same formula which we have learned in our initial classes, b minus a plus 1, right? So if we put these two things in b minus a plus 1, we will get n minus 1 minus I minus 1 plus 1. So finally we will cancel this 2 and we will get n minus I minus 1. So what will be our optimized code? So first we will sort the array, right? And just after that we will run a loop from I is equal to 0 to n minus 1, and we will check whether that a of I is equal to n minus I minus 1 or not. And if we get this, we will understand that this is a noble integer and we will increase the noble integer count, right? So the time complexity of this will be n log n, since we are using inbuilt sorting function, and the time complexity of this will be O of n. So total time complexity will be O of n log n plus O of n. So n log n is the dominant term, so the total time complexity will be n log n. And since we are not taking any extra space, so the space complexity will be O of 1, right? But in the previous question, we have given that we are counting noble integers where data is distinct, which means all the elements must be distinct. Then only we can approach using this technique, right? There is a twist in it. What if the question says that find the count of noble integers where data can repeat? So let's understand that with example. Suppose we have given an array minus 10, 1, 1, 3 and 100. So how many elements are lesser than minus 10? 0, right? How many elements are lesser than 1? Only minus 10. How many elements are lesser than 1? Only minus 10, because we have to check lesser than only, not equal to. So this will be also 1. How many elements lesser than 3? It will be 3 only, since minus 10 and 2 ones will give the count as 3. And how many elements lesser than 100? 4. So how many noble integers are there? This one, and this one. So total noble integers will be 3. We will understand the example 2 after understanding the optimized code on this. First, let's understand the key observation behind the same. So you have to do 2 observations on this. Observation 1. So if element is coming for the first time, which means a of I is not equal to a of I minus 1. In this also, you have to do the sorting. After sorting only, you can perform the steps. This logic will get changed if the data is repeated. So since if you have sorted the array, all the repeated elements will come consecutive to each other. So the 2 observations which you need to do here will be, if element is coming for the first time, which means a of I is not equal to a of I minus 1, right? Which means count of elements lesser than I is equal to n minus I minus 1. And when a of I is equal to a of I minus 1, we simply need to copy the previous element count to the current element. So let's understand the code first, and then we will try run with this example. So in this also, you are sorting the array. So this array was not sorted, suppose. So you will sort it. Okay. Now you will take an answer variable to count the total number of noble integers. Now, if a of 0 is equal to 0, that means we have found one noble integer, right? Otherwise, on the first element, if a of 0 is not 0, we will never find that this is the noble integer, right? So we will run the loop from I is equal to 1 to n minus 1. And if the element is coming for the first time, we will make count is equal to I, right? And if the element is getting repeated, we will check what is present in the count. With that element, we will increase the noble integer count. So let's see with a dry run. So suppose after sorting the array looks like this. So how many elements are greater than minus 3? 0, right? So right now the answer will be 0 only and count will be 0. Since we have started the loop from I is equal to 1 to n minus 1, so our code will reach here, and then we will start from index 1. Index 1 has 0. 0 is greater than minus 3, right? So what is the count of elements lesser than 0? 1, right? Similarly, if we check the next index, the element is 2. So how many elements are lesser than this? 2 elements, right? Since the array is in ascending order sorted, we know that 2 elements are lesser than that. Now we will move to the third element, which is again 2, right? Since this condition will not work for that, we will directly come here. We will see whether this a of I is equal to the current count or not. So our current count will be having 2, right? So we will just repeat the current count, and we will say that we have got one noble element. So in this, when we reach this, since a of I was equal to count, we increase the answer to 1. Then when we move to this 2, we will just simply increase the noble count to 2, right? Since we have repeated the count. Similarly, when we will reach to the index 4, we will get 5 as an element. And we know that only 4 elements are before that. So the total count will be 4, right? But 5 is not equal to 4. So we will not increase the count of noble integers. So this is not a noble integer. Similarly, since the elements are getting repeated, we will repeat the count here, right? And when we will repeat the count, we are also checking if a of I is equal to count or not. So this a of I is not equal to count, we will not increase the noble count. Similarly, here in this 5 also it will not increase, in this 5 also it will not increase. Now we are coming to the index of 8, right? Now how many elements are smaller than 8? 8 elements, right? 0 to 7. All these elements are smaller, right? And 8 is coming for the first time. Now count will be 8 coming from here. Now the next element is again a repeating element, right? So we will check this condition. So our count will not change here. And now since this is repeating element, our condition will check whether that a of I is equal to count or not. What is current count now? 8, right? So this will get repeated here, right? So now since this array element was 8 and it is greater than also 8 elements, so this is also a noble integer. And when we have repeated elements, so that repeated element will also be a noble integer. So our noble array will increase from 3 and then to 4. Now when we will move to 10, how many elements are smaller than 10? This 10 elements, right? From 0 to 9. So count will be I. That means count is 10 right now. Similarly, we will check whether that a of I is equal to count or not, which will again tell that this is also a noble integer. So our noble count will become 5. Similarly, when we will move next index 11, where the element is the repeated one only. So for that, this code will again not work, right? So it will directly come here. It will check whether this 10 is equal to the count or not. And it will also mention that this is also a noble integer. So our answer will become 6. Similarly, for this 10 also will be treated as a noble integer and the answer will be 7. And when we will move to the 13th index, where the array element is 14, which means 0 to 12 elements all are lesser than that. That means count will be 13, right? And since the 13 is not equal to 14, we will not increase the count of noble integers. So the final answer will be 7. So what is the time complexity of this one? O of n log n, right? What is the time complexity of this part? O of n. And what is the total time complexity? O of n log n, since this is the dominant term. And what is the space complexity? Since we are not taking any extra space, so the space complexity will be O of 1. So if you can see, we have reduced our O(n) square logic to O of n log n. And O of n log n is coming from the inbuilt sorting function. So this is also a lead code problem statement. A link I have given in the description as well. Now let's look at how sorting actually happens under the hood. The first algorithm is the selection sort. Imagine you have a row of unsorted numbers. You search for the smallest element in the entire unsorted list. You pick it up and swap it with the element at the front. And then you keep repeating this step for the rest of the array. So you have to find the smallest element in the unsorted portion. You have to swap it with the element at the current front position and repeat the above two steps for the rest of the array. So it will be like pick smallest element, place it in front, pick second smallest, place it in second position, pick third smallest, place it in third position, and continue till the remaining element. So let's understand that with the code. So for I is equal to 0 to n minus 1, you are assuming that ith index is the minimum index, and then you are checking the rest of the array to find any element is lesser than that or not. Now you will run a loop from for j is equal to I plus 1 to n minus 1, and you will check if array of j is lesser than array of min index or not. And you will keep checking that for the rest of the array. And whenever you get array of j as lesser than array of min index, you will mark the min index as j. And once this loop gets over, you will swap array of I with the array of min index. So like this, in the whole array, every time you select the smallest, you can keep it in its actual position. So let's understand with that example. So if you have array 51692, right now min index is 1, right? So after the first for loop is completed, we will get 15692. Since 1 was the min index, so 1 has come to the front. Similarly, now in this remaining array 5692, what is the min index? 4, right? Because 2 is the smallest element. We will again run the for loop for j is equal to I plus 1 to n minus 1, and we will keep 2 in the second position. Now in the step 3, which is the min index? 2, right? So it is already in the correct position. So our remaining array is 9 and 6. Now what is the min index? 4, right? Which is 6. So 6 will come to the fourth position at step 4. So finally our sorted array will look 1, 2, 5, 6 and 9. So now let's finally talk about insertion sort. So to understand this, think of this like arranging playing cards in your hand. So you pick one card and you slide it back into its correct position among the cards you have already sorted. So this will be like shift and insert strategy. So in this, we will start from the second element, right? And we will compare it with the left. If the left is bigger, we shift it to the right, then and there itself only. And we keep shifting it until we find the correct spot to keep that particular element. So if you have given the array 5, 2, 3, 9, 1, so you'll start with the 2. You will keep check in the left whether it is bigger or not. If it is bigger, you will swap the array. So after one pass, 2 will be here, 5 will be here. And now the array will start from here. Here it will check again the left elements which are bigger than that. If it is bigger, you will swap that, right? Now the array is 2, 3, 5, 9, 1. Now you will start with this index 9. You will check whether that 9 is greater than all of them or not. If 9 is greater than all of them, you will not swipe. Now you will check 1 in the last iteration where you will see 1 is lesser than 9. So you will swap it, and after swapping, you will see that 1 is again lesser than 5. You will again swap it. After swapping, you will again see that 1 is lesser than 3. You will again swap it. And similarly, you will again swap it. Finally, we will get 1, 2, 3, 5, 9 as the final sorted array. So what is the time complexity? Since we are running 2 loops, so the time complexity will be O of n square. And since we are not taking any extra space, the space complexity of O of n. But there are best case and worst cases scenarios in this. What if the array is already sorted? If the array is already sorted, then this for loop will never run, right? No swapping will be needed. So that time our best case time complexity will be O of n. And what if the array is in reverse sorted and you have to sort it to its ascending order? That time maximum swapping will be needed. That time complexity will be O of n square only. So only in the best case scenario, time complexity of insertion sort becomes O of n. So let's summarize what we learned today. So we learned about optimization, how sorting unlocks O of n log n solution for complex cost and noble integer problem, right? We understood what is selection sort and how we find minimum and swap it to front. And in the last, we learned about insertion sort, where we picked up one element and kept on sliding it to its correct position. In the next lecture, we will talk about 2D arrays and matrices. If you found this video helpful, please hit that like button. And if you have any doubts, ask them in the comment section. Don't forget to subscribe Techmine Guru for more quality content. With this, myself Supratim signing off for today. Keep coding, keep optimizing, keep learning.